Alright, so this is lecture 10. We're going to go back to our dice simulator. It's our A to D converter, right? Analog to digital. So where we were able to randomly generate the numbers 1 through 6 that represents the side of a die. Alright, but we're going to take a look strictly at the analog portion now because we've gone through the signal analysis and we've understand a little bit better how the 555 timer works. And we're going to take a look at how this takes the 555 timer and puts it into play for us using the oscillation of that timer to go through the digits 1, 2, 3, 4, 5, and 6 over and over and over really quickly, and how it dissipates when we depress the button. Alright, so we're looking at the analog section here, and on the left hand side, right, that's just us pressing the button to roll the die so that we can get number 1, 2, 3, 4, 5, or 6. Alright, and we're going to go through here exactly what happens when we actually roll the die. We're sending out the clock signal. Alright, so looking back at our signal analysis, right, the clock signal is what's going up, down, up, down, up, down, up, down. Alright, so here's a basic schematic of the output of the clock signal from that board. In the upper left hand corner, that's the press to roll button. So that's the push button that we have, and then the capacitors and the resistors that are on here, alright, those are our external RAs, alright, and our external capacitor for the 555 timer. And notice then we have the 555 timer that's sitting in there with VCC, alright, and it has the output of our clock. So the different combinations of these capacitors and the resistors are what changing the oscillation of our clock, and we learned about that last lecture when we went through everything. So a more simplified version. All right, so there's two pictures here. There's one on the left, that's the actual version, so the board that we soldered together. All right, and then on the right's just a simplified version of that circuit. What's really the difference there? Okay, we've removed the R6 resistor and the C1 capacitor. That's really the only difference there with the simplified version. Okay, so when you push the buttons, right, the 100 microfarad capacitor is going to quickly charge to 5 volts through that resistor. Okay, and as long as you are pushing that button, it will hold it at 5 volts. Alright, so it's going to keep going. Then when you let go, so that's when the oscillation starts to happen. Alright, so you'll see when we press the buttons here. Alright, but we can analyze the simplified version. Why are we doing this? Because this was essentially right out of our 555 timer that we did last lecture. Alright, we have an RA, an RB, and a capacitor. So we're fine-tuning those. So we can adjust the period here. And these aren't any new calculations. We did all these before. So the period here ends up being 14.98 milliseconds. And our frequency is 66.74 hertz. So when we analyze that down, what's that really look like? All right, we want to look at the signal. So if we have the oscilloscope on here, and we're looking at the input signal versus the output signal, VC, the voltage across the capacitor essentially is what we're looking at, versus the output voltage of the 555 timer. So notice when the voltage across the capacitor is dissipating, the output voltage of the clock is 0. And I'm looking at the oscilloscope on the right. When the VC, which is the voltage across the capacitor, is charging, the output of the 555 timer, our clock output, is what? It's high. So we can notice, so as VC goes down, V out is at 0. As VC goes up, V out is at 1 or 5 volts. Okay, it's 5 volts. I'm going to deem things in terms of 0 and 1, or on or off, or true or false. But in the actual terms, as VC goes down, V out is at 0 volts. As VC goes up, V out is at 5 volts. Okay, because that's what we have across there. And how do I know that? I'm looking at the schematic. At the very top of the schematic diagram, you see 5V. That means there's 5 volts coming in there. So that's our controls voltage. So that's the basic simplified version. And what are we just creating right there? We're just creating literally a clock, a digital clock, a normal square wave that's just going up, down, up, down, up, down, up, down, up, down. We want that to oscillate a little bit differently. So that's why we're looking at, that's just making a clock signal from a 555 timer. We want to kind of take that to the next level though after this. Because simplified, right? We just look at the period, it's 15 milliseconds, frequency 66 hertz. This is just going to do the same signal over and over and over for us. We want that to change a little bit. So that's why we use the actual version here. Okay? So this is where we have that extra 100 microfarad capacitor and another key resistor in there that's 1.2 kilo ohms. This is going to help change what the signal actually looks like. Okay, so now we're going to add that third signal into the oscilloscope. So the one at the bottom, the limit. Okay, we still have V out, we still have VC, and now we have V limit. So what's really happening here? Alright, so when you push down the button now on our board, and we've all done this, and you can take a look at it, what's it really doing? It's just going through all the numbers really quickly, right? 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. Then when we let go, where it says push button released, this is where the other capacitor and resistor make a difference. Okay, why and how is the big question, okay? Well, one is because, remember that time constant I talked about in signal analysis, tau, right, is RC? So resistor times capacitor. By adding that other RC in there, we change the time it takes for that capacitor to dissipate, which feeds the other capacitor. So we are able to notice how the signal changes. So V out isn't the same thing over and over. It's T high is not the same thing. It's getting longer each time. And notice how VC is taking longer each time to charge. Alright, it's because we're adding that other capacitor. So it's increasing the time to charge. So what's really happening there is instead of going 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6 like it is when we're pressing and holding the button down, what happens when we let go of the button? It goes 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3. And it'll finally, based on the logic, select a number that it's going to land on. Okay, so that's really what's going on here. Eventually that oscillation's going to stop when you have let go of the button for a certain period of time. And based on when you send that signal, that V out signal, that clock signal, so wherever it landed or got stuck in the combo logic, that's the digit that it's going to stop on, right? So we start out, we push the button, and it goes 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4. And you can see that's kind of part C where it honuses in on that last digit and stayed there. It's just like when you guys are playing video games and you hit, you're playing a fighting game and you hit the random button, so it chooses a random character for you. That's really all that that's doing. It's just toggling through all the different possible combinations as quickly as it can. And then once it doesn't get that voltage it needs anymore to change it, and it'll stop when the last voltage is at high. So when V out's high, wherever we're at in the computing process of the combo logic, that's where we're going to get that digit output. All right, so this is really kind of what's going on here as we're taking a look at it. Okay, we can still get the period and we can still get the frequency. Look how the frequency is different from what we calculated before. So this was at time A, all right. This is at time B and time C. So I'm going to step back a couple slides here. Time A is what? When we push the button and we're holding it down. Then time B starts what? When we release the button, all right. And then time C is when it honuses in on that signal. Okay, so let's take a look at this. So this is time A. We're holding the button down, right? So we're not allowing that first capacitor and the resistor in. We're only using the two that are affecting the clock. So the clock signal remains the same. You see that? The output of the clock, it's the square wave at the top. So as the capacitor discharges, we're at 0. Capacitor charges, we're at 1. So that's what it's doing there. It's going to do that forever. Just up, down, up, down, up, down, up, down, up, down. All right? Then at point B, where we let go of the button, this is where the other resistor and capacitor come into play to dampen the frequency. Okay, So what's happening here is that frequency's gone down. Look, before we were at 64 hertz, now we're getting to 36 hertz. What are we doing? We're slowing down the oscillation. Okay, so how do we do that? Notice the period becomes longer. If we look at time A, the period was 15.53 milliseconds and the frequency was 64.36 hertz. When we let go of the button, what's going on here? The period is now longer. It was at 15, now it's at 27. The frequency is what? Almost already cut in half, right? It was 60, now it's 36. All right, so this is at time B. This is where it's still starting to dampen. The signal's going down, slowing down, slowing down, slowing down. And then C is where we finally hone us in on that last value where it gets caught in the combo logic and outputs the digit 1, 2, 3, 4, 5, or 6. What's happening to the period now? All right, now the period's like 15 or 51. So we've gone from 15 to 51. Okay, so the period's gotten longer. And the frequency's gotten what? Slower. We were at 66 originally, all right, then 36-ish, and now we're at 19.44 hertz. So that's what's really happening. Notice how much longer, if we look at the two signals, the clock signal is. See how it's staying high longer, the output, and it's low, okay, for a much shorter amount of time. So now, all right, eventually it's just going to be on at that digit. Look at the capacitor. That's the bottom or the middle wavelength right there, right? Look how long it's taking to charge now. Look how long it's taking to charge, and then when it discharges, it's much quicker. All right, so that third capacitor that we've added in has made a big deal on there. All right, so just to wrap things up, this is pretty much the end of what we're ever going to talk about in here that's analog until we get to the electrical components class. So we've completed, the A to D converter here. We just completed all the analog portion by going through the signal analysis lecture, okay, that we did a couple times ago, and then last lecture we went over the 555 timer, so we understand how a clock signal's created, okay, and then this time we actually took a signal where we're pressing a button and how we're adjusting a clock signal so that it oscillates and then dissipates, and we can focus in on one output at a specific time, and that's going to affect our sequential logic and our combo logic that we're going to start learning about in the next couple of lectures. Alright, so make sure for this one we'll just do some analyzing in class. We might have one or two questions here on your lecture quiz on this one. Not tons of notes, not a bunch of new equations or anything like that. But alright, I will see you guys in class.